Hi there, Turgeon here, bringing you physics from afar. Triangles. In particular, we're looking for a certain kind of triangle, and in physics this is really useful. You want to be able to look at these three triangles and immediately start to see a certain pattern, and that pattern is you're looking for right triangles. Look at these three and decide which among those are right triangles. As usual, pause the video as you need to. In this video, I'll be covering four main things. Actually, it's more like one main thing, which is how to break down a triangle and how to figure out everything you need to know from a triangle using physics trigonometry, I call it. Basically, it's using Pythagorean theorem and sine, cosine, tangent ratios. You should take notes, and like all good note taking, you've got your main body, and then you've also got like extra notes, which are things like questions or your own way of writing things or insights or anything of that nature. 4 items to the agenda. First is the big questions. These are the things that come to mind for the very first unit, which is introductory to the entire year, and it's all about how to be successful. It's all about what is the nature of this class. Math is useful in the course, and you should wonder how. Here's what I consider the key question. If you look at a vector like this, a vector is just a quantity that has a direction. 20 meters per second, 40 degrees below the horizontal is how we would describe it in words. How far does this vector extend horizontally and vertically? There are innumerable times during physics where we want to know how much of a vector is horizontal and how much of it is vertical. We call that components. Write down the word components. I'm not going to give you an official definition. You'll kind of learn it from context. Write down the word components. Here's my example. Here's the part where I do the traditional teaching, and I look at this and I'm immediately thinking, okay, there's a ratio for this triangle. This triangle is in a family of triangles that has this particular shape. Once you say a 37-degree angle, this is a particular shape. This is a right angle over here. Anything that I draw that looks like a right angle is a right angle. The right triangle again. So there's only one family of triangles that has this particular shape. And because there's only one family of triangles that has this particular shape, we can immediately think of in terms of sine, cosine, and tangent. SOHCAHTOA. By the way, background noise. Got renovations, dog. They're paving my road, so they're trucks. And the dog is triggered by the trucks and the renovation. So there's a family. When we say sine is opposite over hypotenuse, we mean there's a particular angle and it's a right triangle, so we always know that the ratio of this opposite side, opposite the 37-degree angle, and the hypotenuse, always going to be the same. That's the key. We're talking about similar triangles here. So I'm trying to figure out these two pieces. You could also ask, like, what is this angle? That's a 53-degree angle. So step one, I'm going to attack it with the sine ratio. SOHCAHTOA means sine of the angle is opposite over hypotenuse. So means sine opposite of hypotenuse. So x is unknown. That's the opposite side. The hypotenuse is known to be 18. Plug this in your calculator. Make sure you're in degrees and not radians. How do you know? Say this out loud to yourself on a quiz. Say this, well, maybe in your head, say it out loud. 37 degrees. And then you're not going to be in radians. You're going to make sure your calculator is in degrees. That gives me the answer. Sorry, these are x and y. We're trying to say, like, I just chose arbitrary labels. Actually, I don't love my labels because y is more of a vertical quantity and x is more of a horizontal quantity. So that was a poor choice. Cosine of 37, why? Because this side, when I look at this, as it's related to the 37-degree angle, that is adjacent to the 37-degree angle. This is still the hypotenuse. That's always going to be the hypotenuse, regardless of how it's in relation to this 37-degree angle. So the cosine of 37 is some ratio, which we know, and that's equal to adjacent over hypotenuse, y over 18. Do a little bit of algebra, do this on your calculator, literally plug in cosine of 37 on your calculator. You're going to get some form of a decimal, multiply that by 18, do the algebra, you get 14.38 meters. Don't forget units in every answer in physics. Now here comes another totally different kind of example. Now we know the two legs of the triangle. This is a leg, this is a leg, this hypotenuse. We know the two legs, and now we want to know this angle. And we want to know the hypotenuse. Well, the hypotenuse, I'm going to call it V. And I'm going to say we're trying to find this angle here. Why am I calling the hypotenuse V? Well, because it's unknown, and these two are hinting to me. This is something you want to do a lot in physics. These two are hinting to me that they are a velocity. So therefore, this is a velocity. So I can simply use Pythagorean theorem to find V. V is the hypotenuse. How are you supposed to know that? Because here's the right angle. The hypotenuse is opposite that. You get 3.6 meters per second. Makes sense, it's bigger than the other two. Now to get these this angle here, I'm thinking about sine, cosine, tangent. To me, I think of tangent ratio because I look at this angle, and if this is opposite and this is adjacent to the angle. Now you might say the V is also adjacent to the angle, but that's the special one called the hypotenuse. I'm going to write tangent of the unknown angle is equal to opposite over adjacent, which is 3 over 2. Now, you can't just do tangent of 1.5 on your calculator. That doesn't make sense. What you now need to do is you need to ask your calculator, what is the angle that will give me the ratio 1.5 when I plug it in? And the way to do that is on your calculator, you write tangent to the -1 of 3 over 2. You type that expression, however you do that, usually with a shift. I like to call that 1.5. It's easier to enter. 56.3 degrees is the angle. And I can't remember why I did these three. Oh, I was just trying to show, like, if we were drawing this in vector form, this would be an upward component of a vector, which actually should be a little bit bigger. This would be an upward component of a vector. This would be a leftward component of a vector. So that would often be represented. You would often draw this like so, and some people like to draw it like so. Try that. Make sure you get the 56.3 and that you're not in that you're in degrees and not radians. Okay, so now you can pause the video and you can try to figure out everything possible about these two triangles. The screen's cut off, but this just says 20 meters per second over here, and this is 17 meters per second. So pause the video, try to figure out whatever you think is logical about those two. And here comes the answers. If I prepared the next slide, I can't recall. So what you should be able to get here, this part is really easy. You just know that those two angles are complementary. And this reveals itself to be 65 degrees. This part, I'm not so sure yet. This part down here, which we'll call x, I'm going to, in order to find, let's find the hypotenuse. So the hypotenuse, I know that sine of 25 is opposite over hypotenuse, so it's 7.6 over h. And now you do some funky algebra, and when you do some funky algebra, you end up with a hypotenuse of 18 because you actually have to do 7.6 divided by the sine of 25. And for whatever reason, I didn't get the hypotenuse here. I think I probably just used, you could get the hypotenuse using sine theta again, or you could use Pythagorean theorem. It's going to be greater than 18. I just didn't bother for some reason. And this one here, you could get this hypotenuse using Pythagorean theorem, and you get 26.2. And you can get this angle using the tangent ratio, what you can call the opposite of the tangent ratio, but don't call it the inverse of the tangent ratio because that's more of a cotangent. This is called the arctangent, technically. And when you use the arctangent ratio, you get 49 degrees for theta, 49.6 degrees. So back to our key question. How far does this vector extend horizontally and vertically? Well, when you draw these in, make a right triangle out of it. This piece completes a right triangle. And when you do the right triangle trigonometry to get these two components, you get 15.3 meters per second horizontally, also to the right, and you get 12.9 downward. This brings up these concepts of vector, scalar, magnitude, direction. That's not pronounced scalar or scholar, it's pronounced scalar. A vector is something that has a direction. Mass does not have a direction, for example. Scalar, mass is scalar because it has no direction. Everything has a magnitude in physics. Anything that we could measure, including the temperature right now, that has a magnitude, but temperature has no particular direction. Another key question, which I am sort of, is like a segue into what's coming later, is if you look at a physics formula such as this one, I equals V over R, what do they really mean? What are they trying to say? So to summarize, right triangles are wicked important, and you need a set of skills and strategies to see the right triangle, see how to break down the right triangle, or build it up using Pythagorean theorem, sine, cosine, tangent, ratio. This has been Physics from Afar.